In this video, we're going to talk about electronic circuits. This is the modern topic in electrical engineering, is how to build circuits that actually provide a power gain. We're going to talk about them, though. We're going to have to talk about a new circuit element, the so-called dependent source. We'll introduce that. We're going to show how those are used to model what are called operational amplifiers. These are the workhorses of what are called active filters. And the word active here has to do with providing a power gain. It's all about power. So let's see the difference between an electrical circuit and an electronic circuit. So an electrical circuit, like we've been talking about, can't provide any power gain. Now, if you figure out the transfer function between some output variable and the source, you may well have a case where the gain is bigger than 1. However, when you attach a load resistor to it, for example, to try to get that power out, it turns out the power that's dissipated in the load has to be smaller than what's produced by the source. Easy way of seeing that, the only thing in this circuit that's producing power is that source. And we know from the conservation of power that all the other elements have to dissipate, or not dissipate at all, but have to dissipate power. So you pick any one of them, that has to be less than what's the power that's being produced, so no power gain. So it would seem like, when you look at the conservation of power, that there's no circuit that could produce a power gain, and that's true, but we're going to introduce a new circuit element that has that capability. And so our new circuit element is what's known as the dependent source. Okay, so here's the idea. We have a circuit, and I'm drawing an abstract thing. Somewhere inside there's a circuit element that has a voltage V defined for it. Somewhere else in the circuit is a voltage source whose voltage depends on what the voltage across that element was. How this happens is a mystery. Somehow this voltage source knows exactly what this voltage over here is and produces something that's K times it. That's why this is a voltage-dependent voltage source. Now, this is clearly not something that you could build just out of raw elements. How in the world can you have such a thing? And this really points out that these are ideal circuit elements, and they're used to describe something a lot more complicated. How this actually gets built, I'll show you an example in a second, and it's not very simple, but it can be well described by our ideal circuit elements, as we'll see in a second. I want to also mention that you can have all four possible configurations here. We have a voltage-dependent voltage source. You could have a current-dependent voltage source. You could have a voltage-dependent current source, and you could have a current-dependent current source. Turns out the last one is particularly important for modeling transistors. So, they are fundamental to characterizing transistor circuits, in particular those circuits that have a power gain. Let me show you how that's possible. So, here's a very simple circuit, split in two pieces, has our voltage-dependent voltage source, and because it's in two separate parts, they don't interact with each other except by this mystical dependent source. It mystically somehow figures out what the voltage is across that resistor. Now, let's do a little power calculation. I think it's pretty clear that all the power dissipated in that resistor is produced by that source, and all the power dissipated in that resistor is produced by the dependent source. Okay? Well, let's draw a little box here. Okay. So, what's the power that's produced by the voltage source? Well, that's got to be what's dissipated in the resistor, so we know that's Vn squared over R. It has to be producing that much power. How much power is being consumed in our resistor over here? Well, that's kVin squared over R. And I really do mean the same die of resistors here. So if K is bigger than 1, which it certainly is allowed to be, this circuit is producing more power than is coming into it. There's a power gain. So what's going on? I thought this wasn't possible. And the answer is it is possible if inside this circuit is somehow being provided with power that's not indicated. And this gets into the idea of what's called a power supply. And these days for cell phones and things like that, you might think that's equivalent to a battery that provides power as part of its functioning so that this circuit can provide the indicated power gain, because the power supply is an additional source of power for the output. How that happens, that's why the dependent source models are used, because they're very simple ways of describing somewhat complicated circuits. But in general, circuits containing dependent sources can produce a power gain. And here's an example of one. But here's a practical example, and this is the operational amplifier I mentioned earlier. So the operational amplifier, its jargon name is op-amp. It's the way we refer to them as an op-amp. And the circuit symbol is indicated here to the left. It has this triangle that has a plus and minus input, which I've labeled, I'm thinking here of nodes. So that's node A and node B. And down here's the reference. The output comes out the end of the triangle, and that's node C. And that's we're going to plug that into a circuit in just a second. The model for it, in terms of ideal circuit elements for the operational amplifier, is as follows. There's a resistor Rn between the two input nodes, and here's our dependent source, voltage-dependent voltage source, that is some gain times the difference of the two voltages here. And that's why EA corresponds to the plus, and why EB here corresponds to the negative side, because that's how they enter into this formula for the voltage produced by this voltage-dependent voltage source. It's all written in terms of node voltages that are referenced to the, taken with respect to that reference. Finally, there's an output resistor, and this is the output. Okay, so what does an op-amp look like physically? This is an op-amp. We do a little counting here. There are 1, 2, 3, and 4 inputs that have to be available for an op-amp. Well, this is a chip that you will see in all kinds of circuits, and this is a short name for an integrated circuit. Which different names for the same thing. Chip is what we commonly refer to it. And notice it has 4 pins over here, and it turns out there are 4 pins on the other side, giving a total of 8. Well, that's more than enough. It turns out it needs 2 other inputs to make the chip function correctly, and the remaining 2 are not really used. So what's inside this chip that can provide the power gain and is modeled by our dependent source model? Well, I think you'll be a little surprised by the complexity. So, this is what's inside what's known as a 741 op-amp, operational amplifier. It contains 22 transistors 11 resistors, 1 diode, and 1 capacitor. So this is the symbol for a transistor. And here's another one. Here's a really odd looking one over here. 22 total transistors. And so it is a very complicated circuit inside to provide that gain. And let's go through what the inputs are. So IN plus, that's node A in my diagram. IN minus is of course node B. Here's the output, which is node C. And these are offsets, which are additional inputs, which we're not going to talk about here, that have to do with detailed functioning of the op-amp. But what I want to really point out are these two, VCC plus and VCC minus. Standard notation for the power supply. Turns out for this op-amp, the power supply has to be about 15 volts. So these are providing additional power to the circuit, which allow us to use the dependent source model. If these are turned off, you take the battery out, it no longer looks like a dependent source. In fact, it probably looks like something very dull and boring. There's the output either is flat, which means it's 0, or it has some distorted waveform. It doesn't function like it was designed to. You have to turn on the power in order to make the circuit come alive and be described by our ideal circuit models. Now, I want to point out that this diagram, this circuit diagram, what's inside, came from a website at Texas Instruments, which is a well-known worldwide producer of chips of all kinds, analog and digital. And this is the website they provide for you to download specification sheets. That's what these are called. I took this from the specification sheet for a 741 op-amp. And you can download and look at all the different kind of circuits and chips rather that they provide and see how they operate. And we need to look at more detail to see what's special about an op-amp. In other words, I want to know something about Rn, Rout, and G. I know the op-amp functions this way, but what are those parameters? Well, let's dive into the specification sheet for our 741 op-amp. Here it is. And what you'll see listed in general are a bunch of different parameters that describe how this circuit behaves, and we'll go through those, but I want to point out something very important. Notice that what's specified in this specification sheet is a minimum and maximum value and a typical value for every one of these parameters. So the manufacturing process guarantees that the circuit will be within these minimum and maximum values for whichever parameter you're talking about. But what it is exactly will vary depending on which operational amplifier you pick out of the batch. So this raises an issue in circuit design. Suppose I want a circuit with a very well-defined gain. You can't get it by just using an op-amp as it is. We're going to have to put circuitry around it to make it function and behave exactly like we want, not like the manufacturer can sort of approximately tell us it's going to behave. We're going to see that in just a second. Let's go through and see how the various parameters of our model are for a 741. So I'm going to point out here Ri, what the spec sheet calls Ri, turns out corresponds to Rn in our model. And the specification sheet says that the typical value is 2 megohms. And it could be as small as 0.3, and the maximum, it could be bigger. But the point is that this is big. That resistor is big, and it's in the megohm range, more or less. And that turns out to be a good thing, as we'll see. Okay. Let's go on to the output resistor, which is labeled RO, output resistance. It is typically 75 ohms. So it's small. And that's good. Okay. Now here comes the goodie. And the large signal differential voltage amplification constant, that's G. The typical value is 200, but look at the units, volts per millivolt. So what this is saying is that it's 200 times 10 to the 3, typically, which means that the gain can be about 2 times 10 to the 5th, 200,000, but it could be as small as 50,000. Well, this, to me, says that the gain is big, which has important consequences. So, big gain, big input resistor, small output resistor. There's something else about the operation of the amplifier. It has to do with the power supply. And this is worth pointing out. So, the critical parameter here turns out is maximum output voltage swing. How big can this voltage at node C be? Okay. And it turns out it depends somewhat on the value of the load resistor, which you're going to attach out here. But notice it's about equal to the power supply voltage, plus and minus 14. Okay, let's take the big number. So suppose the output voltage, C, so we got G times some voltage equal to 14. And what's that voltage? Well, if you divide this out and you use the big number, you get 70 microvolts. So the largest that the input could be, if you stuck it in node A, is 70 microvolts. If you exceed that input, what's going to happen? If you put in a sine wave, and because we want the circuit to work in a linear way, our output is going to be a sine wave. But if its amplitude is bigger than 14, what's going to happen is that the output's going to get what we call clipped. The amplitude will be chopped off. So that's not good. That means sine wave in, something looking more like a square wave out. That's a clear sign of distortion. So how do we handle this? The point is, the threshold voltage for the clipping phenomenon is pretty small. And that's where the external circuitry comes in. We have to learn how to use the op-amp in the context of surrounding circuitry to control it. But the big thing that's going to be very important to understanding that is that the gain is big. We'll see how that works in just a second. Okay, so here's the classic op-amp circuit, the reason op-amps were developed. Here's our circuit model, and I've now stuck that in the circuit. And I have a source and I have my own resistor that I'm using. Here's the load, and here is our F. What does the F mean? What does the F signify? What do you think? Well, F is for feedback. That's where it means it's providing the input to the output. Now, one thing to notice here is that the op-amp is put in upside down. So notice this is plus and minus up top. Notice here it's minus plus, and that's intentional. You'll see that in a second. Also, note that the plus side, node A, has been tied down to the reference. Okay? And node B is where the input voltage is coming in. Okay. So it maybe becomes a little bit clearer when we use the circuit model for the op-amp and stick it into our circuit. Okay. So the way that works, here's Rn, and we'll define a voltage V across it, and because the op-amp, if you will, is plugged in upside down, the output is minus GV, where G is this big positive gain that I showed you in the previous slide. Okay, now that I have the model for my op-amp that's been turned on, I need to find how the input and output voltages are related to each other. We need to solve the circuit. What we're going to use is the node method, because it can solve anything. The dependent source means, the presence of the dependent source means we can't use the serial and parallel rules. Voltage divider and current divider, they're gone. So we have to use node method. That's why we introduced it. Turns out so we could talk about this circuit. Okay, how many nodes are there? Okay, what I get, there's 1, 2, 3, and 4, and of course here's our reference node. Pretty obvious. Well, this node has a voltage source attached to it, so we don't need to define a node voltage there. It turns out the same thing applies to the dependent source, because there's a voltage source between that node and the reference. We don't need to define a node voltage. So the only voltages we need to define are V, that node voltage, and that node voltage, which turns out to be V out. So we need to write the node equations. So here they are, and let's go over one of them. The first one I've written here applies to this node right there. So let's see, the current going south is V out over RL. The node voltage headed west is V out minus the minus GV, which is the voltage over there, divided by R out, and then finally V out minus V divided by RF. So that's the node equation at this node, and you can check to make sure I got the right node equation for that node. Okay, so it's pretty easy to write. As always, the node voltage has to come in with a plus sign for that particular node equation, and the other ones have to come in with a minus sign. So that all checks, so we're ready to go. We want to find the relationship between V in and V out, which means we have to eliminate the voltage V by combining these equations and simplifying. And the result you get, unfortunately, is not terribly simple, but that's okay. So after some manipulation, what you get is the following result. So as you might expect, the result is going to depend on every circuit element and the gain of the op-amp. So this is where the fun comes. What do we know about the parameters of the op-amp, the circuit model? We know that R out is small, and we know that Rn is big. Well, the critical thing is right over here. So R out is small and G is big, so GRF is certainly bigger than R out. So we can forget about the R out. Well, that simplifies things. That means the RF cancels. So this term in front is R out over G times this complicated expression. Well, because G is big, and all resistors have values basically bigger than 1, all these things are small. And furthermore, dividing them by G is going to make them even smaller, because G is huge, which means we can forget about everything here. All that is negligible compared to this, which leaves us with a very simple answer. So we have found the input-output relationship under the assumption that G is big. So the output is equal to the input voltage times a negative number, which is given by RF over R, the ratio of these two resistor values. Well, this is a very important result, because now we control the gain of our amplifier. By specifying the feedback and input resistor values, we control the gain. So we're not sensitive anymore to the variations in G of R in or R out. They don't matter as long as we have a big input and big gain. This result applies. So we control the gain. Do note that it inverts. Remember, a negative sign corresponds to inversion in electrical engineering. So this is an inverting amplifier. That's the name for it. I do want to point out that if you had put the op-amp in the other way, if you had put it in plus to minus like that, this answer would not have changed. If you note, you can see that mathematically. If I put in a minus G in place of G, which corresponds to putting it in right side up, if you will, this term is still small, and you still would have forgotten about it. However, the result would not have been consistent. The input is going in this side. And if you had plus to minus like this and built it, what would have happened is that it would not have inverted. Instead, what had happened, the output would have hit the power supply values, or positive or negative, and it would not have looked like a sine wave. So it is important that you put the op-amp in the right way. The mathematics, when you figure it out, tells you which way it had to be put in. It has to be put in, if you will, upside down because of that minus sign. So that minus sign is very important. That tells us that the input had to go in the minus side. Okay, so there's another thing to point out, that this result does not depend on RL. So again, it's only these two resistors that determine the gain, and those two values control the negative gain of the inverting amplifier. Now, you may not like the fact that it inverts, that it negates, and I'll show you a little bit later how you can fix that. Turns out to be pretty easy. All right, so we now, because of impedances, that everything follows. If I replace my resistors in my circuit by RLC circuits. Okay, I haven't shown an RL here, or ZL if you will, because the answer, as we just found, for the transfer function doesn't depend on that. And we know right away, I don't have to do any more analysis because of the analogy with resistor circuits, that the transfer function for this is minus ZF over Z. The word active filter comes in because we now can provide a gain. It's active, it has to have the power supply. That's where the word active comes from. So, let's suppose I wanted to design a low-pass filter. And for the simple kind of filters we've been talking about, this is the let's say that this is the transfer function we want. Okay, so let's go over it a little bit. So the negative sign comes in because we know this is going to invert, so we have to live with that. K, what's K? Well, if you look at the denominator when F is equal to 0, then the gain of our low-pass filter at the origin is now K in magnitude. So our transfer function starts out at K. If you look at the rest of the formula, when F is equal to FC, that makes this imaginary number here component 1, which means that corresponds to the cutoff frequency. So we have some FC out here, and so in between we get our nice low-pass filter, where that's 1 over the square root of 2 times K. Okay, so this formula is a little bit different for the RC filter because now I'm going to have to pick element values to fit this transfer function that has some gain but has a cutoff frequency of FC. So how would we do that? Well, one way is just to mimic the formula that we have. We could set ZF equal to our gain because it's upstairs, and we'll set Z equal to that because it's downstairs. Now, what's the impedance? 1 plus J times F, constant times F. Well, that looks like a resistor in series with an inductor. Now, for all kinds of reasons, inductors are not used very frequently in filter circuits. They tend to be larger than capacitors, and we tend to want to shy away from using the inductor unless we really have to. So this may satisfy the, if you built this with a inductor and resistor in series in the feedback part, I'm sorry, in the input part, you certainly would come up with a low pass, but it's not the best way to do it. Let's think about this a little bit. How about this suggestion? Suppose the feedback had this for impedance, and suppose the input impedance was 1 over k. Well, that means it's a resistor, the value 1 over k. And the question is, how do you interpret this thing? And what that's telling me is that I have two elements in parallel, because 1 over, if you have a parallel combination of two elements, two impedances, that's 1 over Z1 plus 1 over Z2, which will give us the old parallel form of the product or the sum. Okay, so what this looks like is that Z1 is a 1, so it's a resistor, and Z2, 1 over Z2 looks like that, which means it's a capacitor. So this is what I would like to put in the feedback circuit, is a resistor in parallel with a capacitor. Well, right now we don't have very good values here. If we want to gain bigger than 1, that means the input here is a really small resistor, and I certainly don't like this 1 ohm resistor sitting here. But I know the structure I want to head for. I want to put that in the feedback, I want a resistor in the input, and let's just reanalyze it with those so we can make our choices. So here's the circuit I want to consider. There's the parallel combination of the resistor and capacitor on the feedback part, and here's the input resistor. And we know that the transfer function using S has got RF in parallel with a capacitor, value CF, that's the shorthand notation, and it's going to be divided by R, and there's our minus sign. And we start plugging things in, like particularly what's the impedance of the capacitor, and simplify, we finally get this for a formula. Okay, so now let's see, in terms of these three circuit element values, how the transfer function changes. So clearly, at 0 frequency, the gain, K, is RF over R. So those two element values control the gain at 0 frequency. The cutoff frequency is 1 over 2 pi RF CF. So these two control the cutoff frequency, and you should not be surprised by that. This happened for the RC low-pass filter 2. There was a product of R and C that gave us what we wanted. So we can pick element values. We have 3 elements, but we're only constrained by 2 values, so we have some flexibility to pick and get the gain we want and to pick the cutoff frequency we want for our low pass. And this is a very commonly used circuit for low pass filters. Okay, so electronics. What are electronic circuits? They're the ones that provide power gains. They have to have a power supply or a battery that's in the circuit to provide that power gain. Otherwise, you cannot have a power gain with what's called electrical circuits. And that's only possible with a power supply. And most circuits today are designed based on transistors. They could be integrated circuits or chips, but inside they're based on transistor theory. You have to learn about transistors in another course. We're not going to talk about them in any great detail at all. But we have other things we want to do, and that is to understand signals and systems based on designing and using active filters.